This presentation is about the Mars Science Laboratory, in short MSL, otherwise known as the Curiosity rover. It is about the lessons learned in the now 10 years of exploration of the Mars surface. We will discuss the rover design flaws or problems during exploration and what we can learn from them. Now a short overview of the Mars Science Laboratory, Curiosity. It launched in November of 2011 on an Atlas V rocket. Then, after 9 months of travel through interplanetary space, it landed on Mars on the 6th of August of 2012. And it's operational since then. That's more than 10 years of active service, and the original plan of 1 Mars year is more than surpassed. It traveled a distance of around 28 kilometers and up an elevation of 612 meters. That's up Mount Sharp in the Martian desert. It drilled 35 samples and acquired images, around 500,000 of them, with science cameras and the engineering cameras all alike. It returned data equivalent of around 310 gigabyte, and more than 900 science papers are based around Curiosity or with the data of Curiosity. You could say it's a grand success, and it's still going. I now want to talk about a few problems Curiosity faced in the past 10 years, and also during development the engineers faced, and how they fixed them and what we can learn from them. I now want to talk about the system engineering of the Curiosity rover. You see, the most important thing for a big spacecraft mission is redundancy. That means if one system fails, you have a backup systems that can take its place and ensure the survival and still the functioning of the subsystem. The original idea was a single string architecture for 1 Mars year, but because you don't really know the stresses and the problems that could arise in this 1 year, and you're on Mars with a very expensive piece of equipment and other subsystems, they went for a more conservative, safer approach that was a dual string approach. You have 2 fully separated systems that are not really interconnected, so they could work independent of each other and is more safe. Then if one fails, the whole other system is there to back it up. That was the theory. But in practice, it was very hard to accomplish that, and they went with a lot of asymmetric connections between these 2 systems. That means, for example, we have one sensor power that not only provides data for system A, but also for system B. Or you have, for example, a power supply that not only powers a part in system A, but also powers a part in system B. There was not a clear separation of the systems. It was way too interconnected and not really clear how they were connected. It was not good, not very good documented, and the engineers had a lot of challenges, and it was way too complex for testing and even understanding the design, because if you don't know, if you change one thing in your system, what are the dependencies or the interconnections to the other systems? Does the other system still work? Is it fine, or do I have to think about anything if I change one thing in my system? And there was a whole communication, documentation, and approach philosophy that was not really there. And the lesson there is, for the later mission, the Perseverance mission, was make it a real symmetry and do it more simple, straightforward. Don't overthink it. Don't really make the system too complex, and ensure that you have documented every step on the way and every outgoing and ingoing source of interconnection. So there's other parts or other teams of other subsystems can easily understand what you're doing and what are the interconnections there. So the next problem are the actuators. The actuators on Curiosity are for driving the wheels and also the robotic arm. These are small motors. Normally the wet loop actuators are filled with oil and therefore the bearings can move. But the new solution they had in development are these unheated dry loop actuators. But they were not ready in time and only reached around 20% of its design life before failing in the live test. So they failed in testing, were not ready, so they had to fall back on an old stuff that really was not designed anymore for this rover, and also the other systems were not designed to it. Therefore, you get a whole lot of new problems. You need more power for the heaters, so you heat up the motor so it can work. And that meant you have more downtime sleep in winter, around 70% therefore. And also many more thermal needs, the simulation of the performance and the utilization of the cooling system also. So if you heat up the rover, you need to cool it down in other points. And it was way more complex to simulate with so many new heat sources for the rover, and also integration problems. The housings, the bearings, and also the mass calculation was also set and done. And then you changed a very important part of the rover, so everything has to reassembled, reconfigured, and that was not very good. These integration problems were very hard to deal with, and in the end the main problem was in the design phase, that they said, yeah, well, we will have these actuators in time, but they didn't in the end. And so the lesson we can learn from that is that we have to use what you have and not what you're going to have, especially in very critical systems. And the motors that drive the whole rover is a critical system. If it doesn't work, the rover is not a rover anymore, it's stationary. So be very aware of the technological readiness of each component and don't overestimate the development in the future. Now I want to talk about the fault-tolerant wake-up and shutdown design and its problems during operation. First of all, what is a wake-up and shutdown design? The rover works in the day and sleeps at the night, simply speaking. So there has to be a system that wakes the rover up in the early morning, boots up the main compute units, and in the evening to shut it down to save energy and charge up its batteries overnight. So this system not only needs to be redundant in a normal way, but it needs to be single fault resistant. That means if one part fails in the entire system, it doesn't matter what. It's a cable that's broke or corroded, it's a switch that fails, it's a small FPGA that fails, it's a bit flip, latch up event, anything. The system has to recover itself without foreign intervention for any case, every scenario. And you could, yeah, it's very complex to simulate all these scenarios. So the idea, the single fault resistance, is like the design philosophy behind it, and it's very important. So in case of the Curiosity rover, we have a lot of scenarios they came up with and pre-programmed these failure scenarios. And they're very similar to like how a human brain could even work, or what functions or mishappenings can happen with us. It's the same for the rover. For example, the inability to wake up, a alarm clock fails, for example, or breaks. Then isomania is if it fails to go to sleep in the shutdown procedure, or and remains on. Or sleep apnea is if the rover can't stay asleep, the PAM turns on, the RCE at the wrong time. Or narcolepsy is the scenario if the RCE, the rover compute element, unexpectedly powers off while the rover is awake. The PAMs are programmed to turn it back on within a minute. If the RCE switch is permanently broken, the PAM will turn on the other RCE, and if there is a problem with the prime PAM, the backup PAM will turn up the backup RCE using the backup switches. So the newly prime RCE will then initiate a saving mode and following this type of failure to save the whole system and go to sleep. So you see there's a like redundant system and overwatch function of each system over the other system, and therefore it should not fail. And very important here is to test each system in the FPGA design and the standalone testing of the PAMs, these are the power modules, alone and then integrated later. So on SOL 200, something very bad happened. A memory chip failure in the RCE. The rover was stuck in the shutdown procedure as a line wanted to be read out of the memory chip but could not, and therefore it was stuck in an like endless loop in logout procedure and could not shut down. And that was very bad. So the controllers on Earth noticed this by the current status report that the power draw was still up, even though it should be low in the night. So they swapped through hardware commands the RCE, the rover compute element, to the backup system. And well, and they expected it that, yeah, well, we have now the backup system is on and it would work fine, but there was an unwanted behavior invoked, the narcolepsy behavior I described earlier. That means narcolepsy is predefined as if the backup computer is switched on, then as final resort from the backup PAM or hardware command, and this is what I found out, then the rover needs to go to sleep and in safe mode for the next 16 hours and then wake up at the next day and to check its systems again. Now the question is, why did this happen and why they don't expected this sort of behavior from the system? The reason is pretty simple, because they did not test well enough. And the reason for that is because they didn't have the resources and the time. So they had only one fully integrated testbed that contained the fully redundant RCEs and the PAMs. And they only had limited timing slots because they had to share the testbed with other subsystem teams and therefore could not simulate every scenario that they predefined in every way. That means to interrupt these scenarios, to combine these scenarios, and to fully understand every interconnection that they create through such a system. That means you have a lot of resource contention there and fault coupling happening at the same time, and therefore they did not see it coming, and it is pretty obvious why. The fault-tolerant wake-up and shutdown design and this problem that happened on SOL 200 is just one example of a very complex system that was not fully understood and simulated in the real world. In theory it was, and in the small scenario it also was, and like the small standalone testing of the PAMs and the FPGAs, subsystem tests, but not in the full integrated tests. These are very expensive, of course, and very time consuming, but they are necessary. Therefore, an engineering model of the whole system is pretty important, and also to find the time necessary to fully expect the unexpected and find these sort of unexpected behaviors. This is the main lesson I want to give to you here. So now I want to talk about the wheel design of the Curiosity rover. The main challenges are mainly known. You have very rough terrain, sand, gravel-like texture, and also very sharp rocks in the soil that could damage your equipment. It's very hard to build such a wheel, to find optimal mass requirements, so it's not too strong and weighs a lot more than it needs to be, but not too little material, so it does not break apart. And also, like the wear over time, the degrading of the material. The original 1 mass year window and like the few kilometers they were expected are now surpassed by a lot. but you can really see these 28 kilometers on the wheels and on the material. In the beginning, everything was fine, but after a time, like there was small dents and small holes, but these also weren't very concerning. But over time, as the mission progresses and even after the original mission window, these holes got bigger and bigger and are now so-called grooves, which are like parts of the wheel that are lost, that are gone away, and are very dangerous for the movement of the rover, because it doesn't provide any friction anymore, and it can happen that in sandy terrain the rover gets stuck and buries itself if the wheel still spins, but doesn't really get any forwards momentum anymore. And this is a big concern for the rover. The solution they came up with is just, well, let's test different ways of usage and adapt to the environment, and therefore lengthen the lifetime of these wheels. So they have a test dummy on Earth where they fully can test driving potential with mass simulation, but with the whole wheels intact on Earth, and they simulate the gravel, the sand, and even the terrain, like the hills, the rocks that Curiosity has to drive over, and find solutions for these increased wear and tear issues, and really push the system on Earth to its limits to find things that do work or don't work. So if the situation arises on Mars, they have a solution on hand. Well, you can see on the right hand side very rough, beat up wheels. These are coming apart on the top right side, really like a line through the middle, and the wheel sheds itself. This is a mechanism by design, so if the wheel gets too damaged, the rover can, if it has to, drive over a certain angle over a rock and shed the outer 2/3 of the wheel apart from the rover, and can still drive on only the outer ring of the rover. You can see this on the bottom right side of the test rover in the test environment on Earth. And this is like the last resort for the rover to lengthen its lifetime. The other things they adapted is just change up your drive pattern. They mainly saw that the main use and wear were on the back wheels of the rover, because if you drive uphill, more friction and stress is on the back wheels and not the front wheels. So, well, what you can do is just flip the rover around and drive backwards up the hill. So the now new back wheels have more stress, and therefore overall stress is very good distributed around each wheel, and you can therefore lengthen the lifetime as well. Or just drive slower, or even better, avoid the dangerous terrain. Which, with help from the Mars Reconnaissance Orbiter and satellite imagery of the Mount Sharp region of the crater, they could find a lot of paths that are not so deeply inclined, or much safer with less dangerous rocks nearby, and find new drive patterns and ways to get around and still have the mission functioning without endangering it anymore, or endangering it less. As I'm showing you these problems and design flaws of Curiosity, I want to point out that this wheel is not badly designed. It's very good design, but it's really pushed to its limits. The original design was just for 1 Mars year, and by now it's working more than 10 Earth years on Mars, which is a lot, and it's still working very good. And what I want you to take away from this example is that field testing is one of the most important things for robotics and for moving parts. And if you have the ability to simulate it on Earth, where it's safe, where you can test, where you can take risks, then do it. And it's way more important and like more practical than simulate it on a computer. That is fine as well, but go in and into your playground and play with the robotics, play with the limits of the robotics. Because if it is in space and if it's on Mars in this case, you can't really risk anything there, and just adapt your system, monitor it, and then improve your operation and find new ways of operation. And this is what they did here, and it's very well executed by now. After monitoring your system and adapting your design, the next logical part would be to improve it. Of course, we cannot change the Curiosity wheels anymore, but we can learn for the next follow-up mission. The Perseverance rover can build on these 10 years of experience, and therefore because it shares much of the same robotics, the same wheels, the same drive pattern, and is just slightly heavier, but most of the robotics are basically the same. So it can be based on the Curiosity rover and very much improve on its design. The wheels of the Perseverance rover are slightly heavier, slightly thicker outer shell, slightly bigger, so the outer diameter and the curving radius is a bit less, so the stress is a bit less on rocks. It's slightly narrower, so the area on which it drives on is less, so less wear there, and also has twice as many threads, so it has higher friction in sand, but these threads are not just a straight line. They're slightly curved by a natural way, so that sand cannot get stuck in them, and also rocks cannot find a sharp edge where it can get stuck or like pinch out a hole if you drive over them. This just roll away out of the wheel, and therefore there's a lot less stress when driving. And all these new improvements are just by experience and testing it in the field. To summarize the presentation, I just want to say first of all that the Mars Science Laboratory was and still is a grand success. But there were a few problems during development and operation, so we can learn a lot from them. And in this presentation I showed you a few examples of what was the problem and how did they fix it and what can we learn from them. The main parts are to first of all spend more time on the system engineering part of your project, especially if it's a big project over a few years, and improve the simplicity and clarity of your systems and the interconnections. That means very good documentation, communication, and keep your system simple and easy to understand for everybody, and so that in the later part of the development there are very few reiterations necessary and to change up the whole system, so it's very clearly defined and there are less problems later on the way. The second part I want to point out is that a good test environment is key in operation but also in development. So if you have a system, just test it like you normally test it, but also do a full integrated test. So every subsystem together has to function in its way and simulate it in real life with, for example, a flight model of your satellite or rocket or anything, but also to do field tests if you have robotics there. Just simulate the environment, the conditions, and play with your system and your project so you can really get the limits out first and iterate in the development phase very easily and find these weird interconnections and unknown behaviors. And even if you're in operation, keep the testbed still there to test, for example, software upgrades or different methods of operation, so you can minimize the risk and still get the full potential of your system out of there. Third, if you have a problem, first of all, analyze your problem, then adapt and overcome it in operation. So if you have a problem, don't panic, just focus on the task at hand, and maybe you can change up your operation procedure, your sequence, or just avoid the problem at all and go around and still get operational and get the function you desire. That is, for example, in the Curiosity case, just drive backwards to even out the stress. It can be very easy, and if you have a field test at hand, you can even try it without damaging or risking your precious hardware in space. Last but not least, learn from your design mistakes. You have to analyze them and improve your design, and then self-validate that your new design is better. You can do this also in field and test beds, and learn from them, and overall your success rate for future missions or even this mission will increase drastically.